Okay, hello everyone again. I'm Yuming Zhang, a PhD student from University of Illinois Urbana-Champaign, and I'm going to keep talking about adaptive training. For this research, we are focusing on cognitive load-aware virtual reality training platform for safe drone operation in construction. So construction tasks are physically demanding, and this makes construction one of the most dangerous industry. It's being reported that over 1,000 fatalities and hundreds of thousands of injuries happened annually. So addressing this physically demanding task require techniques that enhance the construction safety and efficiency. Unmanned aerial vehicles, or also known as UAVs or drones, are being adopted in construction sectors to help us do tasks like site surveying, 3D mapping, progress monitoring, and inspecting hazard or hard-to-reach areas. So even though UAVs could automate many tasks for us, there are many limitations for UAV systems, like they could not fully interpret complex or dynamic site conditions. And based on that, they could not make flexible task adjustment for a situation-aware management. So human operators are still required in UAV functionality in construction environment, and because of this new responsibility, it introduced new cognitive cost for construction workers or construction or worker operators. It may introduce problems like mental fatigue, operational errors, and finally may compromise the entire construction site safety or efficiency. Therefore, targeted training is essential to reduce cognitive load and prepare operators for efficient UAV control in construction environment, which is complex and dynamic. And as we mentioned, conventional training methods, either offsite training and on-site training, are being widely adopted in construction area, and they're more they focus on more task-specific skill development and routine execution, but they often ignore dynamic cognitive demands during the training process. So there's a knowledge gap that current UAV training in construction emphasizes on task execution but neglect the real-time cognitive load variations for construction workers. And this may limit the learning efficiency and decision-making and operators' performance in complex and high-demanding environments like construction. Therefore, our research aims to develop a VR-based adaptive UAV training system that could use users' physiological signal as an indicator to predict cognitive load and dynamically adjust the training process to improve the users' learning and operational safety. And to achieve this goal, we develop an adaptive human drone training platform based on cognitive load for construction workers. So during the training process, we ask the users to wear a wristband to help us to collect physiological signals like heart rate variability and galvanic skin response. Those two vectors are related to human cognitive load. The raw data are first collected and then cleaned and resampled to help us to make sure a stable inputs, and the clean data are then segmented into short windows, and those data are then fed into the LSTM based neural network, and the output are then go through the fully connected layer to calculate the activation score. for different cognitive levels. And then we normalize those activation scores with softmax to help us to classify users' cognitive load into either low or moderate or high. So with this cognitive load level in mind, we developed another training platform in various simulations. So we introduce cognitive load into the training system, and then adjust the training parameters like task difficulty. For example, if we find that the user's cognitive load is high, which means we need to decrease the training pace or decrease the number of obstacles in the training to help them to enjoy and be more confident about themselves. And if they have a better performance, we may think that, oh, this task is too easy for them. We may introduce other tasks to make it more realistic as the real construction situations. So similarly, we designed another case study to evaluate the effectiveness of this training platform for UAV operation. We recruited 20 healthy individuals, and before the training, we still asked them to do a baseline task, which in this baseline task, we asked them to control the UAV to do a navigation task and follow a predefined path. And during they perform the task, we we recorded the matrix like task completion time, and then we divide them into two groups and train either with or without adaptive training. And then we do a post-training task with the same task as previously, and also record the task completion time. And here's the results for the accuracy of the classification of cognitive load performance of our LSTM model. So from the figure, this confusion matrix, we could find that overall this LSTM model did a great job for classification, and for both the low level and the high level, there's no error was made, and for the moderate level, we could see that there are two cases are being misclassified to high cognitive load. But overall, the accuracy is 92%, which makes the results promising for us to think the predict cognitive load is reliable. And here's the results for task completion time. Task completion time comparison. So here we have the results for before and after training results for different groups of adaptive training and non-adaptive training. We could find that both group task completion time reduced after the training, and the adaptive training group has a better performance in this situation, which means that with adaptive training, it has been more effective to help the users to master the skills that are required for job operation. And in conclusion, the adaptive training platform enhanced the human-job interaction skills in construction tasks through real-time personalized training adjustments. And the study bridges training gaps in construction drone operation by integrating real-time physiological monitoring into the adaptive learning system, enabling a safer, more resilient, and efficient human-job collaboration in construction site. So for future works, we'll introduce new physiological indicators to help us better understand the cognitive load levels for the users or workers, and explore hybrid models to enhance the prediction accuracy and system adaptability. And yeah, same group. Hope you could you could remember some of them, and we may have some collaborations in the future. Again, thanks my advisor and my colleagues and all the funding resources. And yeah, that's all.